All right, this is a really cool one. It's a story about two totally different kinds of discovery, both made possible by the James Webb Space Telescope. On one hand, you've got this super precise, meticulously planned hunt for a single planet. And on the other, you have this massive, sweeping discovery that completely rewrites the history of a giant city of stars. It really gets at the heart of what science is all about, the promise of what we plan to find, and the absolute magic of what finds us instead.
So, it all kicks off with this amazing question, one that sounds like it's pulled right from a sci-fi movie. Could our closest stellar neighbor, Alpha Centauri, actually have a planet? I mean, we're talking about a star system so close that it's practically our next-door neighbor in the grand scheme of things. And that simple, powerful question was the driving force behind a huge proposal to point JWST right at it and just look.
And what makes Alpha Centauri A so incredibly compelling isn't just that it's close. It's basically our sun's twin. I mean, look at this. It's the same type of star, a G2V, with very similar brightness. The scientists behind the proposal even called it our closest sibling star. So if you're going to look for another Earth, starting with our sun's long-lost twin seems like the perfect place to begin, right?
But, and this is a big but, finding a planet like that is a ridiculously hard technical challenge. It's kind of like trying to spot a tiny firefly buzzing right next to a colossal searchlight, but from miles and miles away. The star's own light is just so blindingly bright that it completely drowns out the incredibly faint glow of any planet that might be there. So how on earth do you even start to tackle that?
This really gets to the core of the problem. To even have a hope of seeing the faint heat signature of a planet around Alpha Centauri A, astronomers needed to achieve a contrast ratio of 1 to 100,000. Think about that for a second. That means you have to somehow block out 99.999% of the star's light just to get a glimpse of the planet's glow. It's an insane challenge.
The secret weapon for this cosmic game of hide-and-seek is an instrument called a coronagraph. The easiest way to think about it is like a super sophisticated sun shield built right inside the telescope. You know how you can hold up your thumb to block the sun? A coronagraph does basically that, creating a tiny, perfect artificial eclipse of the star, which then reveals all the faint stuff hiding in the glare around it.
And the plan they put together was just incredibly detailed. We're talking about a high-stakes, 20-hour-long observation. They would point JWST's MIRI coronagraph at the star and just soak up light for almost a whole day. Then they'd use some seriously powerful computer algorithms to digitally erase every last bit of leftover starlight. The goal? To find a planet maybe as small as 5 times the radius of Earth. This was the promise, targeted, precise science, pushing the tech to its absolute limit.
Okay, so hold that thought about the focused planet hunt. Because while that shows one side of JWST's power, another observation reveals something completely different, something bigger. We're going to pivot now from a single star right next door to a sprawling, ancient city of millions of stars that was hiding secrets we didn't even know we should be looking for.
Our new destination, Omega Centauri. Now, this isn't just any old star cluster. It is the biggest, most massive one in our entire Milky Way galaxy. We're talking millions of ancient stars all packed together in this dense, glittering ball. It's a genuine relic from the early universe, and it holds clues about how our own galaxy was put together.
Now, for decades, the old thinking was that all the stars in a globular cluster were like one big, simple family. They were all born at the same time from the exact same cloud of gas and dust. This made them seem like perfect time capsules. But as JWST was about to show everyone, the family history of Omega Centauri is way more complicated than that.
All right, so let's dig into what the telescope actually found. Using its powerful infrared vision, JWST stared deep into the heart of Omega Centauri. It analyzed the light from countless stars, and it revealed that what everyone thought was a single family was actually more like a bustling, complex city with a bunch of different neighborhoods or populations.
To sort through millions of stars, astronomers use a fundamental tool called a color magnitude diagram. It sounds complicated, but it's really just a stellar census. You take each star, you plot its brightness against its color, and boom, stars with similar properties clump together. And when they did this for Omega Centauri with JWST's super sharp data, they saw something totally new.
The chart didn't just show one or two groups, which were already known as the red and blue main sequences. Nope, it showed a third, totally distinct group of stars sitting right in between the other two. It was a population that had never been clearly seen before, so they fittingly nicknamed it the green main sequence, or GMS.
And this newfound green population, it wasn't just a handful of weirdo stars. Not at all. It makes up a full 26% of the stars they looked at. This wasn't some minor detail. It was like discovering a whole new, massive family branch that nobody knew existed, fundamentally changing how we see the structure of this ancient star city. And what's really fascinating is that these different colors aren't just for show. They're like unique chemical fingerprints. They tell us that these groups are different generations of stars, made from different cosmic recipes. For the bigger, brighter stars, the key difference is how much helium they have. But for the smaller, fainter stars, it's about variations in heavier stuff like oxygen and carbon. Basically, they were born from different batches of cosmic dough.
And the differences just keep piling up when you look at the distribution of star sizes within each population. Kind of like a city's demographics, you find even more clues. The red group follows a standard, predictable pattern, but the green and blue groups, they follow a different curve entirely, with a different ratio of big stars to small ones. This is a huge hint that these populations didn't just have different chemistry, they probably had completely different formation histories too.
So this brings us all the way back to the beginning. We have these two stories that seem totally disconnected, right? A super-focused hunt for one little planet and this broad survey of millions of ancient stars. But when you put them together, they perfectly show us the true dual power of a machine like JWST.
The Alpha Centauri plan, well, that represents the promise. That's the power to go after a specific question we already have. Is there a planet right there? It's science that's targeted, it's precise, and it's based on what we think we already know. But then you have the Omega Centauri discovery, and that represents the other side of the coin, the power of pure, unadulterated exploration. This is the telescope's incredible ability to just look at something and reveal secrets we didn't even know were there. It answers questions we hadn't even thought to ask yet. But here's the real kicker. This is where the two stories truly connect. Figuring out the complex family tree of a place like Omega Centauri isn't just an ancient history lesson. When you know a star's generation, its unique chemical recipe, that tells you exactly what kind of raw material was around when its planets were forming. This kind of broad exploration gives us the roadmap for our next targeted hunt.
And that leaves us with the most exciting question of all. The discoveries we make by accident so often become the guide for the discoveries we make on purpose. So as JWST keeps looking out into the deep black, you just have to wonder, what unexpected story from a city of a million ancient stars is going to point us toward our next single, priceless world?